Okay, welcome back to the Cubical Set seminar at the MSRI. And before I introduce our speaker today, I would like to say a few words using the opportunity that Professor Barcelo, who's the Deputy Director of MSRI, is here with us. This pandemic has been hard on all of us, and I just want to say that because of MSRI's quick decision to act decisively and quickly, we can now all come here and enjoy these seminars in whatever form we can still have them. We all, I believe, very much appreciate the leadership that got us here. So as great as MSRI was before it was closed, we appreciate the great decision that led us to be now safe and be able to enjoy the seminar. So if you would join me in, as we always do, silent applause.
Okay. Thank you. Let me also, let me take this opportunity also to say thank you to the organizer of both program, and in particular this program higher category. I think we have been very impressed, both David and I, on how well you have responded to the difficult circumstances and how well you have adapted and how quickly you have adapted and try to make the best out of the situation. We're very thankful for that. And I think the community, the mathematical community at large, owes you a lot, because I think you've indeed made it possible for many people to benefit still from the mathematics that you're doing at MSRI. So we are very happy. We're very happy. Thank you a lot. So that's me also applauding for all of you, the organizer and the participant as well. Thank you.
Thank you. And so I think, at that point, let's do what we came here to do. So enjoy more talks. And our speaker today is Bob Lutz, who's currently a postdoc at the MSRI, and he will speak about discrete homotopy theory and cubical sets.
Greetings from Delaware. Thank you for the introduction, and thank you everybody for having me. I'm always very excited to talk about this material, especially to audiences that are not primarily combinatorialists, because there is a lot that's topological in what we do, even though the methods are combinatorial, and it's nice to be able to address that crossover. There's a title. You've been staring at that for a while. We're gonna have 4 sections. First, I want to talk about the motivations of the theory, because it really does come from sort of a humanistic place, and I think that's important in addressing sort of why we're asking these questions that we're asking. Then I'm going to give the basic definitions. I'm going to talk about 2 surprising applications in other fields, and finally get into cubical sets more formally, or in particular one cubical set that we really care about. So first things first, I put a lot of text on these slides because I figure people can read them at their leisure when they're on their screens. So Xenia Kramer and Reinhold Labenbacher, back in, I think, late 90s, early 2000s, they were interested in studying complex systems that were arising in sociological and technological contexts. And what they were doing was associating simplicial complexes to these complex systems and trying to study these combinatorially. And so complex system is a term that gets tossed around a lot. What do we mean by this? Well, basically, it's a way of assigning like qualitative information to what they call a combinatorial backcloth. So over here on the left, can everybody see my cursor? Is that visible? Okay, I'm going to use that as like a laser pointer. Over here on the left, I don't know if you can see, we've got, this is like a system of internet connected devices. We've got a smartphone up here and a bunch of computers. And so this is a complex system. You have a bunch of, we'll call them vertices, a bunch of devices sharing information. And the way we assign a simplicial complex to this is by declaring every device to be a vertex, and then declaring the simplices to be instances where you have sharing of information. So over here we have, they call it a PC ring, and we have 4 computers that are all sharing information. And so those 4 computers would become the vertices of a 3 simplex. Over here, this was one of the original examples that was used as motivation. We have a search and rescue system. And so in a, I don't know if it was for naval purposes or what, but this one is naval. So we've got a distressed ship, and then we've got all sorts of satellites and helicopters and other boats trying to help. And of course, they're all trying to coordinate. And the way that information is shared, I mean, we can see these directed edges. This is just a graph, but for every, say, n+1 agents here, we would get an n simplex in this complex. And you can also attach dynamical information to these complex systems. And so basically what that means is just like the way that and the amount of information that is being transmitted is changing over discrete time intervals, right? So you would have a simplicial complex that's changing in some way from one time to the next in a discrete way. The way that we want to analyze these systems is by identifying, well, at this point, informally called Q clusters, and especially Q holes. And so a Q cluster will be sort of an area in the system or in the simplicial complex that is well connected, okay? And a Q hole will be the opposite. It'll be an area where things are not optimally connected, or where the sharing of information could be better. Okay, and these are obviously non-technical ideas. We'll define Q holes explicitly in a second. Those are going to be the ones that we care about. And really, if you had to give a short description of it, it would be that Q holes represent structural deficiencies in the system. Okay, so in the search and rescue system, for example, it might be where we could do some qualitative analysis and identify, well, to make the process optimally efficient, we really should have, say, this ship communicating to this helicopter. They're not at the moment, and we could see that that would really make things better. And again, we'll give a technical definition in a second. And the method we're going to take is, well, we're mathematicians, so looking at the simplicial complex directly might be very complicated. So we want to assign some kind of measurement to this. And in particular, Kramer and Laubenbacher were interested in qualitative measures. And so the idea of a group came to the surface. And that's what we're going to do. We're going to take these simplicial complexes and assign groups to them in a combinatorial way that measure connectedness in the system. And we'll skip right past that slide. So at the core, the main object that we focus on is a simplicial complex, right? We've got our complex system coming from some context. We have a simplicial complex now, and we're going to create a series of graphs out of this simplicial complex. And so we have this parameter Q, and throughout the talk, Q is basically going to decide the dimension of the simplices that we focus on. And we're going to look at what we call connectivity in different dimensions, or Q connectivity. And so the Q connectivity graph, I think it's best done by example. So we start with our simplicial complex. Let's say it's this one, K. It's this 2 complex, right? We've got 5 2 cells, a bunch of 1 cells, and then 6 vertices, 6 0 cells, right? And our, let's say Q equals 0. The vertices of gamma 0 are going to correspond to the maximal simplices of K of dimension, in this case, at least 0. And so we can see that the maximal simplices by inclusion are just the 2 cells, right? So for every 2 cell, I'm going to get a vertex of gamma 0. And then I'm going to get an edge between 2 of these vertices if those 2 cells share a 0 face. So in this case, a vertex. Right, and we can see that we get a vertex for each of these 2 cells, and all of these 2 cells have this common vertex in the center. So in fact, they all share a zero face with each other. And so we get edges between all of them. And we get a K5, we get a complete graph. If we change and let Q equal 1, so we vary this parameter, now Q equals 1, our maximal simplices are the same, right? We still have these two cells are still our maximal simplices. So we have those 5 vertices. And those vertices are now going to share an edge if the 2 cells share a 1 face. So if those 2 cells share an edge. And we can see, for example, that this bottom 2 cell does not share an edge with either of these top 2 cells. So we don't have edges here, but this 2 cell shares an edge with these 2 adjacent 2 cells in this pentagon. So we have edges here. And what we end up with is a 5 cycle. Is this making sense? Are there any questions, Chris? This is, it's a lot of words for a fairly simple idea, but I just want to make sure, because this is.
I think we're good.
Okay, cool.
I mean, if anyone has any question at any point, feel free to unmute yourself and ask the question, or write it in chat, and I will give my best attempt to reading it. But yeah.
Awesome, thank you. And then if we let Q be sort of its maximum sensible value, right? It wouldn't make any sense to let Q be greater than the dimension of the complex, but if we let Q equal 2, we get the same vertex set, still the same maximal simplices, but now it doesn't make any sense for 2 cells to share a 2 face, right? So we don't have any edges. It's just an empty graph on 5 vertices. And now we can actually define what we mean by Q holes. A Q hole is going to be, if we pick a value of Q, it's going to be the chordless cycles of length greater than or equal to 5 in gamma Q. So remember that if I have a cycle in a graph, like this is a 5 cycle here, right? A chord is going to be an edge that sort of divides the cycle. That would go, say, from here to here or here to here. That would be a chord, right? Just like a chord in a circle. There is some question of why 5, right? This seems a little bit arbitrary. Well, it's not too arbitrary. So first off, the first cycles are length 3, right? But a cycle of length 3 is sort of optimal. Like if we're thinking about holes in a graph, triangulated or complete graphs are sort of the most connected ones. So a 3 cycle between in the Q connectivity graph is sort of optimal for applications. That says that those agents are sort of sharing as much information as they possibly can. In certain applications, you may care about 4 cycles as well, which is sort of, okay, now if you have a chordless 4 cycle, that's saying that, well, there's 1 or 2 edges that could be in there that aren't. There's some question of should we focus on the 4 cycles. In some applications, it may make sense to do that. Because we end up defining the objects that we care about in terms of cubical grids, which we'll see in a moment, it comes out in the combinatorial wash, it comes out that the 4 cycles actually are trivialized. And this is strictly a factor of the fact that we're using cubes and we're using squares. And we'll be able to see that explicitly in a second. So we're going to declare Q holes to be the chordless cycles of length greater than or equal to 5. Because for a lot of applications, that's what we care about. And also combinatorially, that's what the methods detect. The way we're going to do this is by using homotopical ideas, but in a totally combinatorial context. So let's start that process. The functions that we care about, so we need something to play the role of continuous maps, right from the sphere to our topological space. And instead of continuous maps, we're going to use graph maps. So this audience might be more familiar with simplicial maps. A graph map is just a simplicial map, but the complexes are graphs, so they're one-dimensional. Right? It's a function between the vertices of 2 graphs that takes either edges to edges or it collapses the edges. So it takes adjacent vertices to adjacent or equal vertices, is the gist of it. This is not, so a graph homomorphism is what you get if you, instead of allowing equal vertices, you just take edges to edges. That's a graph homomorphism. This is slightly weaker than that. sometimes called a weak homomorphism graphs. So one of the main objects that we're going to look at is this, this n-dimensional grid graph that I mentioned. So this is the graph. You can think of the vertices as the integer points in Rn, right? And then the edges are just, it's a grid. So down here, ignoring the colors for a second, this is Z2. Z1 is just an infinite path graph in both directions. We get the idea, right? Z3 is a cubical grid, et cetera, et cetera. And the objects that we care about to form our homotopy groups are going to be graph maps from the n-dimensional grid to gamma q. So here we have some simplest or complex k, we're fixing n, we're fixing q, everything is fixed, and we're looking at graph maps from this Zn is taking now the role of Sn of the n sphere, right? And this gamma q is our topological space that we care about. And in particular, we're gonna require that these maps have finite support. And so technically what we mean by that is just that they take a constant value outside some finite set in the grid. Okay. And down here we have an example that I'm sure people have already started looking at. So here we have a 2 complex where I've colored in the 2 cells. We've got 3 2 cells. We can form gamma 1, this 1 connectivity graph out of that, where we've adapted the colors. And here this is just an example of a graph map from Z2 to gamma 1. Okay, and so the way we think about this is every vertex in Z2 is being assigned a value in gamma 1. So these vertices are being assigned the value blue vertex, right? And we can check very easily that it satisfies these adjacency rules, right? Basically what we would be looking for is if blue ever touches red in here, that's bad, because that would mean that adjacent vertices in Z2 are being taken to non-adjacent vertices in gamma 1. That doesn't happen. Blue only touches yellow, yellow only touches red, we're fine. And this has finite support. So we're imagining that this is blue everywhere outside the picture. Basically, blue is going to be the support for all the pictures we see. Okay, so this is continuous maps from Sn to X. Now we have this, graph maps from Zn to gamma q. Okay. Now we can define what we mean by homotopy. So a discrete homotopy is going to be a sequence of graph maps of the type we just saw. So we're fixing n and q again. And basically the rule for these graph maps is that if I pick a particular vertex, like let's say I pick this blue vertex just outside the box here, the box is growing as we go. It's just meant to encircle the support of each of these graphs. So let's take this blue vertex up here. As I go from F1, the first step in my homotopy, to F2 in the middle, I want to pay attention just to this vertex and make sure that as I go step by step, it doesn't break adjacency essentially. So this blue in the next step can only become yellow or stay blue. And if we look at the next step, it turns yellow, totally fine. And in the next step from there, it turns red. So at every point, I'm only going to an adjacent vertex or an adjacent value, as long as I pay attention to the same vertex. And that's all this condition up here is saying, right? Fi of v is adjacent to Fi plus 1 of v, or they're equal. So this is not a particularly interesting or meaningful example of a discrete homotopy, but it's just meant to illustrate the idea, which I think is not too bad. And the fact that it's sort of expanding concentrically from the origin is not necessary. It can do anything at once. One thing to note is that we only care about these graph maps that have finite support. We don't care about what the support is. So notice that the support here is changing, and that's okay. You can even have some like yellow ones pop up outside here as much as you want. The actual support can change. What isn't allowed to change is what we call support value, right? So all these maps are based at blue, and that's not going to change. So for example, I can't have all these outside blue vertices turn to yellow in the next step, even though that satisfies this adjacency condition. We need the support to always be blue. Okay, the idea is that this is a homotopy based at the blue vertex. And with this, all we need is a product. And so let's define the product. So first, we're going to fix a base vertex. So in our gamma cube, pick a vertex in the whatever component we care about. In our examples, that was blue, okay? And now, trust me, the discrete homotopy defines an equivalence relation on these graph maps that we've been caring about, okay? And on the equivalence classes, we can define a product as a very visual definition. So let's assume that here we've got equivalence classes of two different graph maps. Let's assume that the support is contained in this region that I've cut out, okay? So you've just got this plus sign and this cross here. And the way that I take the product of these two classes is I basically concatenate these supports horizontally. So I take the plus and the cross, I put them next to each other in a new grid. I fill all the rest in with blue or whatever my support value is, whatever my base vertex is. And that's going to give me a product. It's not obvious that this is well defined. There's also, right, I'm in 2 dimensions, so there's some choice of how to do this. I've decided to do it horizontally, but what's to say that we couldn't do it vertically? It ends up being the same. You can use it's a simple Ekman-Hilton argument to show that it's the same. But once you do that and you show that these are well defined, which does take some showing.
Bob, may I interrupt you?
Please.
This is Marielle Liverne speaking. In your definition of homotopy, am I right if I think that the map would be always homotopic to the constant blue?
Not all. So these maps definitely are null homotopic in this sense, but it's not always the case. So I don't know if I have any pictures of.
So this is because of your graph. I mean, this is because in sense it's contractible, right?
Exactly. This graph is contractible in a discrete sense. Yeah. So any graph map you have to this graph is going to be null homotopic. Yeah, exactly.
Okay, thank you.
In a second, I'll be able to describe explicitly a non-null homotopic map. I don't know if I have any actual pictures of them though. So
I also had a question about discrete homotopy. I'm Emily Real. So, I mean, sort of classical homotopy but of continuous functions between spaces, you can say a homotopy is itself a continuous function where you take the domain space and you product with an interval. So I'm wondering if you can add a dimension to the graph Zn somehow and redefine discrete homotopy as some sort of graph map.
Yes. So if you don't define things in pictures, that's how you do it. Basically, instead of, you can just define it as a graph map from Z to the n cross a discrete interval, so cross a path graph. And right, all this is saying is that if I cross Zn with a path graph, that this is a graph map. It's respecting the adjacency from step to step. Yeah. So in that sense, it's exactly the same. I thought it was clearer with colored dots. Yes, exactly. So we do get a group. You can take it on faith. And I mean, one thing, I've already sort of emphasized this, but one thing to re-emphasize is that while n sort of plays the same role as it does in classical homotopy theory, right, n determines the dimensions of the sphere, here it determines the dimensions of this cubical grid. Q is a new parameter. Q does not really have any analog in the continuous theory. Instead of determining the dimension of our source space, Q is sort of talking about the dimensions we're picking out of our target space of the simplicial complex. And so we get this bigraded family, and I mean, things can vary significantly as Q varies. It's not as if it's some needless parameter. It really is genuinely new behavior that does not have continuous analog. And we'll see in one of the applications, we'll see where that Q really does come into play. So we mentioned earlier that 5 cycles and greater are the important things in this theory, and that 3 and 4 cycles get trivialized. I think a lot of people will buy on faith that 3 cycles get trivialized. Maybe not immediately obvious why 4 cycles are ignored. And apparently that's something that generates a lot of questions usually. So let's just look at it explicitly. We've been seeing graph maps from Z2. Now let's just look at Z1. So just from the integers, let's take a 4 cycle. We've got the vertices colored in here. And let's take, this is now going to be a discrete loop around the 4 cycle, right? I'm going blue, yellow, pink, green, and blue. Okay, so this is genuinely a discrete loop. And I'm claiming that this is null homotopic, that I can use a discrete homotopy to deform this into a constant map, which is the identity in the discrete homotopy group. And it's very easy to do. So remember, the only thing we have to make sure of is that in each step, I take a vertex to itself or to an adjacent vertex. So here I have yellow going to blue. Yellow is adjacent to blue, that's okay. Got pink going to yellow, that's fine. Green going to blue, that's okay. And blue going to blue, that's fine. And then from here, I think you can see that this map with just the one yellow dot very clearly then deforms into nothingness. So in only 2 steps, we can deform a 4 cycle into nothing. And so when we say that the discrete homotopy theory ignores 4 cycles in gamma Q, or that A1 ignores the 4 cycles, this is what we mean, is that they are not detected in this sense. We get relations for them. And you can do a similar thing with 3 cycles. So this is where the easiest example of a non-null homotopic map comes in, is that if I had a 5 cycle here, and I did a similar thing with a 5 cycle, I put a loop around it instead of a 4 cycle, I would not be able to deform it into a constant map. And that's true of 5 or higher. So that's the simplest non-trivial element we can really describe to answer the question from before. So let's look at some examples. If our simplicial complex, if K is just a simplex, then all the discrete homotopy groups are trivial. Not terribly interesting, but important example. If n is greater than 1, using that same Ekman-Hilton argument from before, you can show that these higher discrete homotopy groups are abelian, just like in the classical case. And the argument is essentially the same, which is kind of neat. And as we've been saying, so A1 is going to detect Q holes of length greater than or equal to 5, but not of 4 or less. And just to really make that concrete, here we saw earlier that gamma 1 of this complex was a 5 cycle. And we see that indeed when Q is 1, A1 is detecting that. We get this non-trivial factor in here. But then when all we have is 4 cycles, everything becomes trivialized. So A1 is trivial. And just as like in the continuous case, if you have a simply connected space, you suppress the base point in notation. If we have a connected graph, if gamma Q is connected, we'll suppress the base point in the notation to make things simpler. Okay, a lot on this slide, sort of disjointed. But first, just to really codify this idea with 3 and 4 cycles, we have this theorem, or proposition, I've called it, which explicitly spells things out. So if you take your gamma Q, this is some graph, right? And let's attach 2 cells to this graph along all the 3 and 4 cycles. That gives us this space XQ. And it turns out that the fundamental group of XQ is A1Q of the simplicial complex. So there's really no mystery as to what A1Q is computing, in the sense that we can build this very concrete, very simple topological space and just take its fundamental group, and that's what A1 is computing. There is the situation for higher groups is more complicated, and that's where cubical sets will come in at the end of the talk. For the special case of graphs, instead of forming the Q connectivity graph and dealing with all this, right, it only really makes sense to do that for Q equals 0. So for graphs, typically what we'll do is, instead of taking maps Zn to gamma 0, we'll just take maps Zn straight to the graph itself and define the discrete homotopy this way. And there's some subtlety of whether we're dealing with the line graph versus the original graph, okay, but but the theory ends up being the same. And I just wanted to sneak this in here to address higher homotopy groups briefly, because there's some question of, well, what do we know about those? So in this graphical homotopy theory, for every n, there are graphs that have non-trivial an. We don't actually know what those groups are, but we know they're non-trivial, they're infinite, and so far these are the only ones in the literature. And also, it's not clear whether these graphs arise as the gamma q of simplicial complexes. So these examples are only existing in the theory for graphs and not really coming from the theory for simplicial complexes. It's important to note. There are examples. Generally speaking, though, what is known about the higher discrete homotopy groups, just like for classical case, is murkier. We'll get to that later in the talk. So we're going to focus basically on definitions in this talk, and sort of structural theorems, but there is a whole theory. I mean, this is legitimately a discrete homotopy theory. It's not just discrete homotopy groups. And so lots of things from classical topology we can sort of port over. We get relative discrete homotopy groups and long exact sequences that behave exactly the same as in the classical case. There is an accompanying homology theory that is extremely rich, and it satisfies versions of the Eilenberg-Steenrod axioms. It plays nice with the discrete homotopy theory for graphs. There is a discrete Hurewicz theorem. So this is a homotopy, or this is a homomorphism from the discrete fundamental group to the first discrete homology group, whose kernel is the commutator subgroup. So exactly the same. And we get spectral sequences, which I am not qualified to talk about. So next slide. We won't get into any of this now. This is just to say, if you are interested in this, just be aware that there is a body of work surrounding this. It's not just a list of definitions. Okay, we get to our first application, which is super nice. And this application sort of planted the flag for discrete homotopy theory in pure math, right? Originally, it came from these applied contexts, and these theorems sort of said, like, no, this has applications that are of real interest to pure mathematicians. So we're going to start with the finite real reflection group W, and the simplicial complex that we care about in this case is the Coxeter complex of type W, and we're going to be focusing on a particular class of subspace arrangements. Okay. We start with what are called parabolic subgroups, which are a particular special type of subgroup of this real reflection group. Right, every subgroup is going to be made up of reflections, and so to each subgroup, I can associate the subspace that is fixed by all the reflections in the subgroup. Right, and so the subspace arrangement, the collection of subspaces that we care about, is going to be, we're going to fix a parameter k, take all the rank k-1 irreducible parabolic subgroups, it's a mouthful, and associate to each one of those subgroups a subspace, and that collection will be this WNK.
Let's mention, Bobs, that this is over the real, correct?
These are real reflection groups. This is an Rn, or maybe Rn minus 1.
When the case k equals to 2 is over the complex, it's generalized. So it's, in the end, the result will be really general.
At this moment, though, it's only over the reals. The complex case comes in the next slide. And so these, you may not have a great handle on what these look like, but there are familiar examples that these generalize. So when k equals 2, we get the familiar Coxeter hyperplane arrangements, right? And they also generalize the k equal arrangements, which are higher codimension generalizations of the braid arrangement, okay, the type AN Coxeter arrangements. So these are two important classes of examples of these W and K. Lots is known about Coxeter arrangements, so these results really become interesting when k is greater than or equal to 3 in the non-Coxeter cases. The theorem is that if we take any of these subspace arrangements, we look at its complement in this real space, and we take the fundamental group of that complement. Well, this is over the reals, yeah? Yeah. So we take the fundamental group of that complement, that this topological object is actually isomorphic to this discrete fundamental group of the Coxeter complex. So this completely combinatorially defined object. And this is where this parameter Q really shines, right? Because that's what's being changed as N and K are varying over here. So this is really where the one application in this talk where Q does come to play and does end up being very important. So this is sort of a extremely surprising theorem. I mean, in general, the fundamental groups of complements of subspace arrangements are very complicated. And it's very surprising that you end up being able to define it in terms of relatively familiar object. There's one consequence of this that I want to talk about in particular. So we get a real version of a classical result of Brieskorn. Let's just recall that a finite reflection group admits a presentation of this type where we have this generating set S. All of our generators have order 2. That's what this first relation says, right? This involution relation. And then we have the braid relations. So this is saying if I have 2 generators, S and T, if the order of ST is 2, then S and T actually commute, okay? If the order is 3, then STS equals TST, and so on and so forth. We get relations for 3, 4, 5, etc. So there are infinitely many here, but only finitely many may apply. So the theorem of Brieskorn, rephrased a little bit in terms of the generators and relations, says that if we take the Coxeter group of type W, or Coxeter arrangement of type W, excuse me, and we take its complexification, so we look at the same linear equations, but over the complex numbers, right? And we take the fundamental group of the complement of this complex arrangement, that the group we get has the same generators and relations without relation 1. So we get rid of these involutions, and we're just left with the braid relations. That gives us a presentation for this fundamental group. A surprising and beautiful result, and lots of people thought so. That paper is highly, highly, highly cited. We actually get a real version of that from these discrete homotopy techniques. And the real version is that now instead of K equals 2, if we let K equal 3, and instead of looking at the complexified version, we just look at the real subspace arrangement, right? So if you think the complement of a real hyperplane arrangement is not very interesting topologically, right? But if we now let K equals 3 and we have codimension 3 subspaces, or codimension 2 subspaces, excuse me, the fundamental group of the complement can become very interesting. And so the fundamental group of this real space now is given by the above generators. Instead of forgetting relation 1, now we're only going to keep relations 1 and 2 and get rid of all the rest. So all we have is the involutions and these commutators, and we get rid of all the other braid relations, and that gives us a presentation for this pi 1. I mean, this is as nice as results like this get. This is a like stunningly, this is like an exquisite, I love this theorem. It's very cool, and you know, it makes you wonder what happens for higher values of K, but it seems unlikely that you would get anything so nice, I guess. I don't have much else to say about that, but.
Bob, for higher values of K, they become trivial, correct?
So in fact, the presentations become very, very nice.
It's easy to show that.
We have one of the authors of the paper here, or the person who wrote the paper, fortunately. Okay, so apparently they're trivial for higher values of K. So the special behavior is limited to these 2 cases.
Maybe I can add something just quickly. The reason why also it's easy to see combinatorially why for higher value of k it becomes trivial is that as you augment the k, then your graph you're adding core to your graph. And as you add core, then you get all these 3 cycle and 4 cycle, and therefore your group becomes the discrete homotopy group of that complex becomes trivial.
I see. You're adding chords to the Q connectivity graph of the Coxeter complex. I see. That makes sense. Good. I'm glad you're here. Said something very false. Okay. Our second application is group theory. And this requires a slight generalization of the homotopy groups. So just focusing on graphs in this case, no Q parameter. Whereas before we were dealing with graph maps, right, which require that all the images be distance at most 1 apart, right? They're equal or adjacent. If instead of requiring distance at most 1, we relax it to distance at most r, some parameter r, now instead of graph maps, we're dealing with, say, R-Lipschitz maps, where we think of the graph as a metric space, right? We get a generalization, it's A and R. We have this extra parameter now where things are a little bit relaxed. And so we have this fact from group theory, you might remember from grad school or advanced undergrad maybe, that if you have a free group of finite rank, and you have a quotient of that free group, that you can recover the normal subgroup that you've modded out by looking at the Cayley graph, right? So let's say the scenario is we have this free group and we have the quotient, but we want to know what the actual subgroup is that we've modded out by. For some reason, we lost that information. What we can do is take the Cayley graph of the quotient with respect to the image of our original generators, and take the fundamental group of that Cayley graph. And that's going to be some free group, right? And that's going to be isomorphic to N, to that normal subgroup. Okay, there's a very nice fact about free groups. The problem is it doesn't extend to other groups, right? Well, if you only focus on continuous homotopy, that's certainly the case. But discrete homotopy can do this for any finitely presented group. So by finitely presented, we mean we have a group of this type where S and R here are both finite sets. Okay, and basically the same thing works out. The only extra thing you have to worry about is this parameter R. So there is a value of R depending only on the generators and relations of the group, so that if you look at the discrete fundamental group of the Cayley graph of the quotient, you recover the normal subgroup itself. And there's the extra qualifier that your Cayley graph now might not be connected, right? And so you have to look at the component that contains the identity. But this is, I mean, surprisingly in the paper of Delaby and Kukro, this isn't even listed as one of their main results. It's just a lemma. But as lemmas go, this is, I don't know, pretty significant and nice. One thing that's nice about this value of R is that it doesn't just depend abstractly on the generators and relations. There's an explicit formula for how big it has to be, and you could just compute it, which is very nice. So those are two applications. We have probably 2 minutes. Can I take 5 more minutes? Is that all right?
Sure. We have, okay. Yeah.
We haven't gotten to cubical sets yet, and I'd like to spend a couple minutes on them. The name. So this is now the cubical set section. And there's a question of what do we want? Well, we mentioned earlier, we have this nice proposition, right, that in order to compute A1 of a graph, all we need to do is add 2 cells to the 3 and 4 cycles of the graph, take pi1, and we've got it. Right here is an example that looks like a fancy sock or something. So it's like we've got a bunch of 3 and 4 cycles, we add 2 cells, take pi1, and we get the discrete fundamental group. This is a really nice result, and it makes communicating what A1 computes very easy if I'm talking to people who aren't familiar with this kind of thing. What we want is something similar, but for the higher discrete homotopy groups, right? That would be really nice. So that's the goal, is to construct a topological space whose continuous fundamental or continuous homotopy groups agree with the discrete homotopy groups of the original graph. Okay, unlikely that it's going to be as simple as this, and it turns out it's not nearly as simple. But this is where cubical sets come in. So first, let's define cube graphs. So a cube graph is exactly what you think it is. We'll define it as a subgraph of the grid. It's the induced subgraph where all the coordinates are 0 or 1, right? So you can think of this as the discrete unit cube in Rn, if you like, or the one skeleton, okay? We'll fix a graph G, just like before. And the cubes in our cubical set are going to be the Hom sets. Okay, so here, I guess the category we're working in is graphs with graph maps. Okay, so these are Mn is going to be the graph maps from the n cube to G. So different ways of putting the n cube graph into our graph G. And to make a cubical set, right, all we need now is face maps and degeneracy maps. And so let's define those. First, let's define some graph maps on cubes. So these maps are going to do exactly what you might anticipate that they do, given that you've been in a cubical set seminar for several weeks now. So here, this takes the n-1 cube to the n cube, and it's a face map for the graphs, right? It's taking the n-1 cube into the epsilon, to the 0 or 1 face of the higher cube. And this one is now taking the n cube onto one of its faces. Right. So Mn, remember, is this Hom set. And of course, we get induced maps. So A induces a map now from Mn to Mn-1. B induces this map beta that goes the other way. And as you might expect, these become our face and degeneracy maps. We obtain a cubical set. I got to use this cube symbol, which I was very excited about. Right, so this is a contravariant functor, and our face maps are, as we said, they were. I'm being a little bit abstract about this because, I mean, one of the things is we're not topologists and we don't have a great intuitive understanding of what this space looks like. So when I think of this space, I think about it in these terms and not too much more. I mean, this is sort of where I'm at with it. So the theorem is that if we look at the geometric realization of this cubical set, this is the space we wanted. Okay, the continuous homotopy groups of this geometric realization are exactly the discrete homotopy groups of the graph. So eureka, right? Except there's an asterisk in the theorem. Okay, so it's very important to note that this is a theorem under the condition that this, what we call cubical approximation theorem, holds. And so feel free to read this. It is almost exactly the simplicial approximation theorem, but phrased in terms of cubes instead of simplices. Here we say cubical map. A cubical map is the same as it's hard to find an actual definition on the internet. I don't know, maybe this is this like a typical term, cubical map?
I think we understand what is meant.
Okay, yeah, it takes cubes, it takes the vertices of cubes to cubes that may be smaller. Okay.
Right. The only thing I would add is that 2 weeks ago in this very seminar, Tim Campion announced something that sounds like the cubical approximation theorem. So I should probably push you in touch.
Yeah, please do. Okay. Well, maybe this is no longer proposed. That would be extremely interesting because, I mean, this has been one of the goals of the theory for some time now, is to get this proven. And I know that, I mean, Helene knows more about the history of it, but several people, I think, have tried to prove it. And I think it's been hard.
Several topologists have tried over the years. We first put it on the not on Slack, but well, now I'm having a blank. Anyway.
Map overflow?
In the what?
Map overflow? Or,
yes, thank you. Thank you.
Okay.
Map overflow many years ago. And over the years, there were announcements. I think one of the first one was a student of Max Karoubi. There was announcements, or we found it, and it never held. It always broke. And so it would be very exciting if this year, you have it. That would be very exciting. One person to talk to would be Eric Babson, correct? Because he's been also. I mean, certainly in the beginning I tried, so I'm definitely not a topologist, and I tried a little bit to understand the subtlety and understand how this could work, and I realized that this was definitely out of my league, and I have the most respect for Eric Babson, who's a definite, strong, in my view, very strong topologist, and he's been looking at that also from time to time. I mean, he hasn't thought about it for a long time, but in the beginning he really tried to prove it and hit the wall as well. So it would be very exciting if it's proved.
I mean, I wonder if some of the difficulty has something to do with minimal cubes category. I mean, isn't one of the things that we've been learning? So there's lots of different categories of cubes that we've been talking about over the course of the semester, and all categories of cubes have the same object. So it's, you know, there's a cube in each dimension. But the question is sort of what maps do you allow between the cubes? So do you consider symmetries? Do you embed, do you have like diagonal edges inside the higher cubes? And I think part of the motivation for introducing these kind of more exotic cube categories, historically newer cube categories, is because they kind of more closely mirror what sort of the geometric intuition. So in the minimal cubes category, which is our name for the one that's being used here, there's certain cubical sets that I don't remember off the top of my head, but I'm sure Chris does, that ought to be contractible. And if you geometrically realize them, you get some very weird space. So, I mean, I could imagine as a consequence of that this cubical approximation theorem is false for this particular category of cubes.
Mm. I see.
Right. So maybe a quick comment to make. I mean, maybe this is like obvious to everyone else, but I'll just say it anyway. So the thing is, yeah, the problem with the minimal cubical sets is that when you take the product of the interval with the interval, you get, and you geometrically realize it. So you have a canonical geometric realization where you take a cubical set to topological space. So the interval times the interval, you get S1 wedge S2, which is very much not contractible. However, there's a solution to that, which is instead of Cartesian product, take the geometric product. Now, if we look at the product that we're taking here for the relation of homotopy, right? Like the product that we're taking, when you look at this grid, like the grid doesn't have those diagonals that you would have in a Cartesian product of the graph. So it looks to me very much like the geometric product, actually. And the geometric product fixes this problem somehow. So I'm wondering if there's something there that might work.
Like
I don't know. That's just a
graph Cartesian product corresponds more closely to the geometric product. Because that's all the grid is the right, it's the graph Cartesian product of the
exactly, yeah. Yeah. So you get the square
I'm not
rather
sure
than
the grid. I mean, right. I guess because you're using graph. It's the graph Cartesian product if you use graph maps, but not if you use graph homomorphisms. But I guess because you're using maps, it is.
Exactly. Yeah. Okay. Anyway, maybe we should let Bob continue and then have more discussion after. But I think it's getting exciting.
Some of these may apparently be answered, but we'll find out in due time, I guess. So first question is that theorem true? Which you sort of covered. Second question is, right, we've got this infinite dimensional CW complex, this geometric realization, sort of a theme in like combinatorial approaches to graph braid groups and other homotopy questions, are whether we can find nice deformation retracts of spaces. So it seems unlikely that a finite dimensional retract would exist, but something along those lines where we could get rid of, you know, a lot of the cells that don't matter would be nice. One other thing would be if we could use this approach to directly find non-trivial higher discrete homotopy groups. That would definitely be useful, because right now the method is very indirect. And then whether or not this could be used and sort of as a bridge to take some of the tools from continuous homotopy theory that don't exist in the discrete homotopy theory, of which there are a lot. Lots of things just don't have nice translations, to sort of prove some of these dream theorems we might want, like the Hurewicz theorem for higher dimensions is something that's been worked on, and the Dold-Tam theorem for symmetric products is something that, again, we can prove in like the low dimensions, but not for higher cases. So those are sort of the big questions that we're asking right now, and that's it. So thank you, everybody.
Okay, thank you very much. So we're doing the usual silent applause, not to mess up everyone's mics, as it often happens. But yeah, okay, so now we know what the last, the penultimate slide.
Just, yeah.
I see, okay. Yeah, okay, so I'll open the floor now for questions, comments, or anything else that you'd like to add. Maybe, okay, maybe I'll ask something. So what about pi1? Is the, what do we know about pi1 in general? So, for instance, something like Van Kampen. Do we know Van Kampen?
Yes. Oh, I didn't put that in, did I? Yes.
Maybe you said it, I just missed it. I'm sorry.
Oh, no, I didn't. I made that slide today. I forgot to put that in. Yes, there is a Seyfert-Van Kampen theorem. And it, I think it works pretty much exactly the same. Is that right, Helen?
Yeah, you have to be careful. Am I unmuted? Yeah. You have to be careful about your intersection. You cannot break cycle, correct? So when you take the intersection, you have to be careful that you don't have a cycle that span, you know, it has to be entirely in the intersection. It should not be broken, you know, in two pieces, because then you're going to lose some of your homotopy. So, but yeah, it's similar. You have relative homotopy theory also, and you have, yeah.
Well.
Yeah, so I mean, that's one of the sort of the broader goals of the theory, right? Is you have an exotic homotopy theory. What do you want to do? Well, you want to try to take all the stuff in Hatcher, right, and do it for in the discrete case. Well, because if you're going to prove more complicated theorems, you need this sort of basic toolbox. And one interesting thing is that a lot of these properties often fail. Like there's the homotopy extension property. Is very important when you're trying to prove basic theorems in algebraic topology, and it just doesn't mean much in the discrete case. It just sort of fails very quickly. And so, I don't know, for a lot of things like that, you need workarounds, and it's interesting to see where things do correspond and where they fall apart.
Okay. Any other questions? Comments? Maybe I'll ask quickly. Sorry, I don't want to like steal everyone else's time. But what about something like homotopy excision, Blaker's Massey theorem?
So that is in my paper that I referenced. That's the future questions section of that paper is, can we do this, right? Because the goal has been to prove Hurewicz in higher dimensions, which obviously is the Blaker's Massey is the usual tool to do this with. And that's where totally unclear. So, I mean, if you try to mimic the argument that's typically used, it's unclear like what the analogs should be or how to port these homotopies over. That's partly where like homotopy extension property and things become important. Just these very basic things we take for granted that fall apart. And again, you know, in improving Hurewitz or Blakers-Massey or anything, you're using approximation theorems sort of pretty liberally, and that's not a tool that we really have at our disposal, so they require workarounds. So right now for the Hurewitz map, we have like, there is a Hurewitz map possibly proposed, and we can show it's surjective in a lot of special cases, but injectivity is a total question mark. Yeah, and that's where excision would come in. Yeah.
I'll ask one more stupid question, and then I'll really shut up. So, Whitehead's theorem. So I think that's an interesting one. Like if you Whitehead's theorem. So if you induce isomorphisms on all homotopy groups, are you a homotopy equivalence?
Also an open question in that paper. Unclear, and part of the reason is we don't have an excellent handle on the higher discrete homotopy groups, and this was one of the goals of the current project, but there is, I can tell you personally what I think. I personally think that it fails. And this is because the notion of contractibility in the discrete sense, so what that would mean is, right, the identity map on the graph is, because you can define discrete homotopy for not the grid, just like graph maps from G to H or whatever. And so, right, if you take the identity graph map and try to discrete homotope it into a constant map, that notion is extremely rigid. And in general, the notion of homotopy equivalence of graphs is very restrictive. And so graphs that you might look at and think, well, those should be homotopy equivalent, like a 5-cycle and a 6-cycle. In some philosophical sense, right, those should be homotopy equivalent, and continuously, of course, they are. They're homomorphic. But in the discrete sense, they're not homotopy equivalent. So my suspicion is that no, and that there are tons of examples where it doesn't work out. One graph that is not contractible that I suspect has all trivial discrete homotopy groups is, so take the 3-cube graph and add a diagonal in. It's not contractible in the discrete sense. So it's not homotopy equivalent to a point, but I suspect that it has all trivial homotopy graphs. That's not necessarily an opinion that's shared by everyone on the project. That's my personal belief, but I suspect that it fails very badly in an interesting way. Bad in a good way.
Yeah. I had a conjecture, but after after learning more now from you, I think my conjecture was just plainly stupid. But no, I'm wondering. So yeah, if there's a model structure that one can put on it, and then Whitehead's theorem is something, and yeah, it's just a statement about homotopy equivalences versus weak equivalences in the model structure. So I'm wondering if that's a statement about like there being very few covariant objects in that model structure. But I think that may be a bit too naive. But Okay, maybe I'll just shut up. And
It's up my end, that's for sure.
I mean, if homotopy extension's the problem, it suggests like few fibrant objects, or that's what I would have thought.
Oh, my guess was kind of those 3 and 4 cycles, that they are an obstruction to cofibrancy. But as I said, it was too naive. But yeah, I think it's a good point about, yeah. Fibrancy. Huh. Yeah, maybe there's very few any nice objects. Okay. So, do we have any further questions?
Yeah.
Oh.
So, first of all, thank you. I really enjoyed this talk, and I am really interested in how the sort of cubical nerve of these graphs realizes the homotopy type. But I'm wondering, do you know if there are any other kinds of cell shapes other than cubes which would be able to model the homotopy type in the same way?
So I know that, and Helen, you certainly know more about this. They have built similar theories not using cubical grids, is that right? Using like hexagonal something, or was that for homology?
Yeah, well, I'm not familiar with anything that would have been built with different for homotopy. Homology, I'm not sure either. I mean, I know the Yao group that has done the graph homology, I'm having, which is with word, and it's a directed graph, and but that doesn't actually, the cube plays a bigger role than not in there. So no, I'm not aware of that. No. Curtis is on there also. Curtis, are you aware of anything like that?
No,
yeah.
Nothing to add, sorry.
Yeah. So, yeah.
Yeah, so unknown, I guess, is the, if you think you see a direction, it may be worth pursuing, you know.
I didn't have any specific one in mind, just curious.
I thought I remembered at one point we had discussed that there was like building a similar theory on some other kind of like a hexagonal lattice or something. I don't know that I ever had a specific reference for it. It might be where there's a, as Solen mentioned, Yao has like a school of people working on this stuff. They call it path homology, is that it?
Yeah, yeah.
And they've built,
yeah. So,
they've built a homotopy theory.
You know, and they built a homotopy, but the path homology at the beginning, they also, and we thought the same with them, because they showed that the H1, their first homology group, their first path homology group, is indeed the abelianization of our discrete fundamental group. So then you may think, oh, therefore their description, their creation of this path homology is going to be a good homology for the discrete, but it's not. It's breaking after dimension 2 and higher. The homology group are not the same, and they are not, so they don't satisfy the Steenrod axiom either for the discrete fundamental, and so they are actually distinct homology, distinct object. Yeah. So
one thing I do know, and this might be like baby town stuff to people in your field, I know, but if you build homology in the way that this cubical homology is built, but with simplices instead, I think it was Curtis, you told me that this ends up being the same as singular homology, no? Or was it singular?
Yes.
Yes, that's right.
Curtis discovered that.
Instead of cubes, you use simplices, you end up with the same thing. So I wonder, you know, if there's some invariance under like similar shapes or something, like if you used octahedrons or something, you would end up with the...
I'm really, really sorry, but I do have to leave today. I'm already 12 minutes late. And
okay. Thank you for staying.
I'm very thankful that you gave us this opportunity. And today is a day where I have to be at MSRI, like I said in the beginning, to sign some check for you guys. But I have a few other things I have to do before they go, and they want to go. And so I'm sorry, I'm gonna have to leave. Okay.
Thank you for joining us.
Yeah, thank you. Thank you so much.
Thank you for the checks.
Okay, maybe, yeah, final call for questions and.
Maybe one more.
Okay.
So you mentioned that you found examples of graphs which have non-trivial higher homotopy groups.
Yeah.
But do you have any sense of which homotopy groups you're able to realize in this way? Like, could you construct graphs having any higher homotopy groups or only some?
So the way that I found those was, we know there's a paper of Ellen and Curtis and some other people who they found graphs with non-trivial discrete homology. And we're actually able to compute that the homology groups were Z. And so for any n, you'll get a graph whose nth discrete homology group is Z. And I used a natural map from the nth homotopy group to the nth discrete homology group, and showed that for this class of graphs, it was surjective. And the thing about that argument is that it does not really extend to any other classes of graphs. It was like very ad hoc. And so I don't know that we have really any intuition. The methods we have right now are not flexible, if that's what you're asking. And so in order to come up with other examples or sort of have a better control to say like, okay, pick some parameters, can we find something with non-trivial or whatever, is not, I mean, for any n, we do have a graph with non-trivial an. So in that sense we do, but it's not clear, say, like what properties about those graphs contribute that behavior. I mean, the intuition behind those examples is basically like, so, right, to construct spheres, continuous spheres, you can just take suspensions, right? Take a sequence of suspensions. We can define suspension just as easily for graphs. You take it, you cross a graph with a path graph, and then just contract the bottom and the top parts, right? And you get a graph. And that's exactly how these examples come about. So you start with a 5 cycle that has non-trivial A1, as we saw. You take its suspension, take a sufficiently long suspension that has non-trivial A2, take a suspension of that, that has non-trivial A3, and so on and so forth. The only thing is the length of the suspension matters, because you have to decide what the length of your path graphs is that you're crossing with, and the lengths of the suspensions get longer and longer and longer as you go. It's sort of an interesting aspect of it. But so, I mean, again, our intuition for that, I think, came from, I mean, Curtis might be able to speak more to this, but came from the continuous theory. You have to work around things like, I don't know, not having a hop fibration, which is usually, right, the connector between, like, proving the non-trivial higher homotopy groups. And so you have to find, like, sort of, I call them like junk methods, but there's very ad hoc ways of getting around stuff like that.
So you don't expect these sphere graphs to relate in any expected way to the homotopy groups of spheres?
Probably not. But again, like, intuition is so minimal that it's hard to say. And that's sort of the nice thing, is that an affirmative or a negative answer would both be equally interesting at this point, because nobody knows anything. But no, like if I had to spiritually, no, I think they're probably D. Another thing is, like, let's say we take the nth suspension of the 5 cycle or whatever. We don't know what the lower homotopy groups of that are. We don't, like, they should be trivial because it's a sphere, but we don't know. And we don't have any way to show. Yeah.
So I guess Eilenberg-MacLane spaces are not obviously known. Yeah.
Not at all. Well, okay. So one, for as far as kpi1, I did prove in that same paper that if your graph has no 3 or 4 cycles, that all its higher discrete homotopy groups are trivial. So if you have no 3 or 4 cycles, you're like Ka1 or whatever. So that's something, but beyond that, no, I don't think it's certainly not for higher than 1. It's not known. Yeah.
Okay, I should really read your paper. It seems like whenever I ask, the example or statement is already there. So.
Yeah, but see, that makes me feel better, because it means that my research intuition is matching up with somebody in the outside world, which is always good. Cool. Well, that's all I have. I'm gonna go make meatballs.
Okay, so I think it's meatballs time. So let's thank Bob again for the great talk.
Thanks, everybody.